Hello, I'm Thomas. Welcome to my presentation about instant neural graphics primitives. This was joint work with Alex Evans, Christoph Schied, and Alex Keller. I want to start with a motivating example of why you should be excited about neural graphics primitives. What you see here is a so-called NeRF model, which is a 3D reconstruction of the shape and appearance of objects from a few dozen photographs. In our framework, you can train this reconstruction in seconds to minutes, and afterwards you can explore it interactively in real time, as you see here. Having such a reconstruction at your disposal, you can do many really cool things. For example, you can do computational photography, where by editing the properties of the virtual camera, you get realistic defocus effects and can frame your shot perfectly. This is not just some AI blurring the background, this is ray tracing through a virtual camera to produce the same blur that you would see in the real world. You can also extract geometric feature buffers that can be used by downstream tasks, like density distribution, surface normals, 3D position, or depth. As I said before, all you need to do to train this model is capture a video of static objects, and in this case, a person holding very still, and then extracting a few frames of that video. What I'm visualizing right now are the viewpoints of the frames that were used to create this particular reconstruction. One more example, you can slice and manipulate the 3D construction to focus it on just one particular region of interest and then keep working from there, for example for compositing. Hopefully this piqued your interest. We are now going to look at what neural graphics primitives are and how they can be trained and rendered instantly. Simply put, a neural graphics primitive is an object whose shape or appearance attributes can be retrieved by queries to a neural network. For example, given a position x in 3D space, as well as extra parameters xi that depend on what kind of object we're talking about, we can pass them through a neural network, which will then output corresponding attributes that describe the graphics primitive at that location in question. I realize that this is a bit abstract, so let's look at a few examples. A 2D image is a graphics primitive that can be described by a function mapping x on an image to its corresponding RGB color. To turn this into a neural graphics primitive, we simply replace the pixel lookup with a neural network. Admittedly, for typical images this isn't very interesting, but if our image contains billions of pixels, a neural network can be a quite compact representation of it. What you see here is a zoom in, while one such neural gigapixel image is being trained in real time. Another graphics primitive are signed distance functions. Here, given a 3D position x, the function returns the distance to a 2D surface, where that distance is positive on the outside of the surface and negative on the inside. Again, one might consider training a neural network to represent this function. Here you can see instant training of such a neural signed distance function. The first half of the video shows the learned shape, and the second half of the video, which should start in a second, I'm visualizing slices through this function that the neural network has learned, where red means negative values and green means positive values. Another example, radiance and density fields, also known as NeRFs. This primitive also takes a 3D position, but additionally the view direction. The output is how much stuff there is at that particular position, so how dense the object is there, as well as that position's color when viewed from the given direction. To render an image of this representation, you can use ray tracing, simply querying the graphics primitive at a bunch of steps along the ray and compositing the result. What's really cool about this is that with recent advances in differentiable rendering, you can backpropagate through this rendering process and train the 3D representation from 2D images only. So it's effectively a 3D reconstruction from video. Just like other graphics primitives, we can train this one in just a few seconds. You can even go one step further and train a neural graphics primitive directly from a light transport simulation. This is called neural radiance caching. Normally, you create photorealistic images by simulating billions of paths of light, but in neural radiance caching, we can trace way fewer paths and use those not to render the image, but to train a neural network that then generalizes the illumination throughout the scene. In this video here, all the colors that you see are the output of one such neural radiance cache that is being trained online from such a light transport simulation. As the camera moves around, you can see the neural radiance cache gradually learning more detail wherever the camera looks. For example, here you can see the shadow of a tree. And as the camera approaches the shadow of this tree, you can see the shadow of individual branches and leaves slowly appearing. This is the online training of the radiance cache. After having seen all these examples, let's summarize again. A neural graphics primitive is an object represented by a neural network that takes a query as input, usually a position as well as extra parameters like the view direction, and returns appearance and shape attributes. But why should we use a neural network in the first place? What's the difference to classical voxel-based volumetric representations? Well, the main downside of voxels is their impractical memory usage, which grows cubically with resolution. To be fair, if we're talking about just a 2D surface in 3D space, we can get around this limitation by building a tree or hash table. But this introduces extra complexity and does not handle the general case of truly volumetric data. Another limitation is that voxels tend to be rigid, hard to animate, and limited to just 3 dimensions of space. Incorporating extra axes of variability, like how the appearance changes under different view directions, typically runs into the curse of dimensionality. But hey, voxels are really fast. Typically just a single memory lookup. It's really hard to compete with that. Neural networks trade this large memory footprint for compute, and they're more flexible than voxels are because you can just add extra dimensions of variation, like the view direction, time, or latent appearance codes, by concatenating these dimensions with the input vectors. So far, the main argument against neural networks has been how slow they are. But this doesn't have to be the case. If you limit yourself to relatively small neural networks and you're careful about making good use of your GPU hardware, in our case running a homegrown machine learning framework, you can get those neural networks surprisingly close to voxel lookups, because in the time it takes to go up the memory hierarchy after incurring a cache miss, the matrix multiplication hardware, which starts to be reasonably widely available, performs thousands of operations, right? Even more importantly, we don't actually have to choose between voxels and neural networks. Prior work in the last 2 years has shown again and again that a combination of the two tends to give the best mix of quality and performance, and this is also what we are going to make use of. So we've built instant neural graphics primitives on top of 3 pillars that each provide roughly an order of magnitude speedup. Importantly, these speedups all end up multiplying, which gives an overall roughly 1000x speedup compared with a native implementation. First, it's worthwhile to write dedicated rendering and training algorithms for the graphics task at hand. For example of Nerve, recall that you render an image by marching along a ray. The smaller the steps along which you march, the sharper the image will be. But a good rendering algorithm will skip over all the empty space until the object is hit, and once the first couple of steps have penetrated the object, the following steps should also be skipped, because all the stuff further along the ray will be occluded by whatever has been hit first. In our particular implementation, we take 10 to 100 times fewer steps than naive dense stepping, which means that you need to query your network 10 to 100 times less often. This does need control flow and dedicated code to make efficient, so we found that dense tensor-based algebra wasn't actually all that applicable here. Next, I mentioned before that by specializing on small neural networks and tailoring our implementation to them and our hardware, we can outperform existing frameworks by up to an order of magnitude. And you can see now why I said before that these speedups are multiplicative, right? We have 10 times fewer queries to a 10 times faster neural network for a total speedup of 100x already. The last ingredient is going to be a quote-unquote good input encoding to the neural network. The idea behind input encodings is that the inputs can be translated into a form such that they're easier to meaningfully process for a neural network. This can, again, improve quality tenfold at the same neural network size, or conversely maintain the same quality with a much smaller neural network, which again amounts to a multiplicative speedup. But more details on that later. First, I want to give a quick overview of what we call fully fused neural networks and why they can be faster than the networks implemented in established frameworks. Let's say we limit ourselves to multilayer perceptrons, which means some number L of fully connected layers with M neurons each, value activations, and no biases, just for simplicity. The key observation is that the compute cost of such networks scales with the square of the number of neurons, while their memory traffic scales linearly. Normally, this means that we need to focus on compute. But for the really small networks we are interested in, the memory traffic actually dominates because modern processors have a much better constant factor for compute than for memory, and the complexity class just doesn't have all that big of an effect for small numbers of neurons. It turns out that for sufficiently small neural networks, you can structure the computation in such a way that you can evaluate the entire neural network without ever leaving the local caches of the chip. So the only accesses to GPU RAM are loading of neural network inputs, loading its weight matrices, and writing its outputs. For those who are familiar with operator fusion, it's basically that, but taken to the limit. Here you can see the resulting performance as compared to TensorFlow. These plots show the throughput plotted against batch size. where the left plot shows inference and the right plot shows training. On the left of these graphs, you see throughput for small batches, and on the right of these graphs, throughput for large batches. For inference, we're interested in processing large amounts of data at a time, for instance, all the pixels of an image, and there we are roughly 8.6 times faster. For training, we are interested in small batch sizes, because if we have a fixed amount of training data, we'd rather take many small optimization steps than a single large step, just to converge more quickly. In this case, the speedup is again roughly 9x. If you're interested in more details, there's a paper about fully fused neural networks in the context of radiance caching, and there's also a corresponding GTC talk from last year at the shown link. In the remainder of this talk, I'd like to focus on the good input encoding. Let's first have a look at the kind of positive impact that input encodings can have in general. Here you see real-time training progress of a regular neural network, moderately sized with 10 layers, 128 neurons each, and the performance optimizations I mentioned before applied already. So multiplicative speedups, fully fused neural networks, all in there. It looks quite bad, doesn't it? Now let's make a tiny modification. Now we are encoding the inputs to the very same neural network using the frequency encoding of Mildenhall and colleagues. This frequency encoding amounts to evaluating sine and cosine waves at various frequencies. Nothing more, just sines and cosines. The difference to before is incredible, right? Just by passing in the inputs in the right format, the same neural network can extract much more information from them. Now, the question is, how do we go from here and get an even bigger improvement? Other works have already shown, actually, that making the encoding also trainable alongside the neural network can give another big boost in quality, which is something we also make use of in our encoding. This is how our encoding applied to a much smaller neural network looks like. You can see that it's not only faster because the network is so small, but it also trains in fewer iterations and converges to higher quality more quickly. That's because the encoding is now also trainable alongside the neural network. I said before, though, that prior work has already figured out trainable encodings. So why did we make our own? The answer is that prior approaches tend to use dynamic data structures, usually trees, to associate trainable parameters sparsely with 3D space. For example, to focus just on the surfaces of objects. This can work fine, but means that the encoding is somewhat tied to the task. The meaning of a surface entirely depends on what kind of graphics primitive you have at hand. And for many graphics primitives, like NURF, for example, surfaces only emerge as you train. So typically these data structures are progressively refined as training progresses. In contrast to that, our encoding tries to be as general as possible. It works out of the box for all kinds of neural graphics primitives, and is specifically tailored to be efficient on modern GPUs. It works as follows. We start with a query position x. The example here will be two-dimensional for illustrative purposes, but everything generalizes nicely to 3D. Conceptually, our encoding stores trainable parameters on the vertices of multi-resolution grids, here visualized as a blue 2x2 grid and a red 3x3 grid. By multi-resolution? Well, neural graphics primitives often have detail at many scales. Imagine, for example, that you're in a video game where the player is in a room and looks out of a window onto a large landscape. If the neural graphics primitive is meant to, say, learn the lighting throughout the scene, it needs to have fine detail in that room that the player's in and coarse detail to capture the large landscape he's looking onto through the window. If we build an encoding out of a cascade of progressively finer grids, this means that some grid is going to be coarse enough to capture the landscape, and another is fine enough to capture the room. I already hear you ask, Thomas, if you put features on a grid that's fine enough to capture a single room, but still covers a large landscape, won't that grid never fit into memory? And that question would be well justified. Instead of storing these fine grids densely, we just look at the grid cells that contain the query point, we hash their vertices, and this gives us indices into dense storage that we can then size independently from the grid resolution. Or in other words, each grid has a corresponding spatial hash table that has a predetermined number t of entries corresponding to f-dimensional trainable feature vectors. This is a rather different approach to sparsity than tree structures that explicitly focus on surfaces. Why should we do it this way? Well, first, there's no control flow divergence. This is what GPUs are good for. To look up a value, you just compute a hash, derive a memory address from it, and look it up. Every thread of the GPU can do it in parallel. Next, this gives us an easy, predictable way to trade quality for memory usage. And lastly, most importantly actually, This scheme works with any neural graphics primitive and will automatically exploit sparsity in whichever way the task requires it. This sounds a bit like black magic, right? But think of it in the context of an optimization problem. When the hash tables are too small for the resolution at hand, there will be collisions. Multiple points will alias to the same table entry. That's just how sparsity works. But when you're computing gradients for optimization, these gradients will average for all colliding points. So whichever point has the largest gradient and is therefore the most important to the loss will dominate that average and will be prioritized. In other words, just by using gradient descent, the loss function automatically determines where the hash tables focus their sparse detail on. You can think of it somewhat as a soft collision resolution where those entries that minimize the loss the most are prioritized the most at the collision resolution. And again, this works regardless of task, dense or not, surface or volume, just by using gradient descent and letting the gradients collide. We're not done though. In order to actually use these hash tables to learn a smooth function, we interpolate the lookups, for example linearly, in order to produce the neural network inputs. If we wouldn't do this and simply picked the nearest neighbor, the function would look rather blocky. And if your use case requires higher order derivatives than linear, piecewise linear, you can either use higher order interpolation schemes or apply the smooth step function to the plain old linear interpolation. We actually discussed this, how to do this efficiently in more detail in the paper. And lastly, you might remember that the position is not always the only input to the neural graphics primitive. Any extra parameters can simply be concatenated and optionally encoded in some other established value. And then comes the neural network at the very end. That's it. These are all the pieces that we've used to build the instant neural graphics primitives. Putting it all together lets us learn signed distance functions in a matter of seconds. Synthetic nerve scenes also train in a few seconds. And even larger, more detailed real-world scenes can be trained in a minute or so and then explored interactively. What really stood out to us while working on this is how productive it was to iterate on these machine learning models in a matter of seconds. With such a pipeline, the barrier of entry for new experiments is also much lower. If you don't need a day for every single experiment, you can just, say, take a few photographs of your modular synthesizer and just quickly check whether you can reconstruct a tangle of cables, rather than carefully weighing up whether it's worth the extra day or two on your compute cluster to try this out. Being able to freely fly around makes it also much more likely to find interesting nuggets, like, oh, the model reconstructed what's outside of the window? Cool. Or when I zoom out far enough, I can suddenly start seeing that these nerves models actually cheat very much in the distance. It's also worth pointing out that we tried to make the instant graphics components as modular as possible. For example, Munkberg and colleagues were able to just take our input encoding, for which we provide PyTorch bindings, by the way, and use it in their own work as a volumetric texture that helps learn a mesh, materials, and lighting from image observations. To summarize, in order to get instant training and rendering, we had to be mindful of the entire stack, from the rendering algorithm to the neural network and the input encoding. Only by having detailed knowledge about each of these steps could we know that there was, firstly, potential to improve each of them, and secondly, that the improvements would compound multiplicatively in the way they do. For rendering and training algorithms involving computer graphics, it turns out that our GPUs can do much more if we use their fine-grained control flow capabilities rather than trying to express everything in dense tensors. On the neural network front, it turns out that small neural networks are a special case that can benefit from an implementation that makes better use of the underlying hardware than general-purpose matrix multiplication routines. And lastly, in terms of trainable input encodings, we found that multi-resolution hash tables tick a lot of desirable boxes. They can automatically learn sparsity in a task-agnostic manner as a simple byproduct of using gradient descent, and they can therefore be used as a general building block for neural graphics primitives. So does this mean we should all stop using Python and go low-level instead? Of course not, right? Being able to prototype quickly has obvious advantages. But my experience with this project has really been that going low-level is much less of a development overhead than I initially thought, and in some ways actually allows for more flexibility because you can go under the hood of pretty much everything. And obviously, even if you spend more time programming the thing, this can be compensated for when training times are measured in seconds instead of hours. So while we shouldn't drop our frameworks just yet, I think it's worth giving the low-level approach more consideration than you would typically do. Here's a link to all the source code pertaining to this project. It's separated into a homegrown low-level neural network framework as well as a separate code base that does all the neural graphics primitive stuff. I'm looking forward to answering your questions if you have any, and to chatting in general. Cheers!